Hi all, welcome to the lecture on the measurements of airborne particles and on the first lecture that will cover particle counters. My name is Zoran Ristovski. I work at the International Laboratory of Air Quality and Health. I'm a professor at the School of Earth and Atmospheric Sciences at the Queensland University of Technology, Brisbane, Australia. So I'll give a short introduction first, a few words on air pollution, and then on what and how to measure, and then why to measure particle number, because that's what particle counters do, and explain the principle of operation, including some background in important physics concepts needed to understand the operational principles of particle counters. So what's air pollution? Well, air pollution can be divided roughly into two major parts. The gases part of the air pollution, we look at vehicle emission as an example, any combustion source. What comes out is mainly carbon dioxide, carbon monoxide, some oxides of nitrogen, both NO and NO2, and also some unburned hydrocarbons. And this comes more or less from any kind of combustion sources. So in addition to the gaseous pollutants, what is also an important part of air pollution are the smoke or the particles suspended in the air, or what we called general term aerosols. So what are these sort of aerosol and aerosol particles? Let's define them better, because we'll need that to understand as well how particle counters work and what they actually measure. In general, particles or aerosols in the air refers to any kind of solid or liquid larger than a molecule and roughly diameter larger than 3 nanometer, but small enough to remain in the atmosphere for a reasonable amount of time. And meaning that that would infer that the diameter would be around smaller than 100 micrometers. Particles larger than 100 microns settle very quickly in the atmosphere, so don't stay suspended for a long time, therefore will not get transported a large distance and are really not that significant and important. An aerosol is actually suspension of these particles in a gas, so not in a liquid, but in a gas. Where do they come from in the natural atmosphere? Well, the natural atmosphere can be treated like a beacon, chemical beacon. They're mainly produced by pollution sources, combustion, and typical particles that come out, soot or the carbonaceous particles. Fires produce them, either artificial fires or man-made fires, or natural biomass burning, but also significant source of particles are so-called secondary particles, which are formed in the atmosphere by photooxidation processes, and that's the whole sort of chemistry part of the atmosphere, and they come mainly from biogenic or anthropogenic organic volatile precursors. Huge source of airborne particles or aerosols are also the oceans in the form of sea salt, as well as mineral dust particles, as long as they are sufficiently small enough to spend sufficient amount of time in the atmosphere, so as long as they are smaller than 100 micrometers. So we see various sources which would infer also various composition and various properties of the particles. And with the particles, as we said, they vary in sizes from, or the aerosols from 3 nanometers to 100 micrometers. Size really does matter. Particles like gases are characterized not only by the single, let's say, concentration expressed in milligram per meter cubic, like you would characterize for any gas, or a mixing ratio in parts per million or similar, but they also have other characteristics, and that is how big they are, what's their composition, what is their shape, surface, etc. So why is this sort of important at all? As we said, bigger particles settle quicker in the atmosphere, therefore their atmospheric transport will influence the particle size, as well as lung deposition, which is sort of atmospheric transport in a small, and their decomposition also kicks in, makes a significant importance on the particle. So to understand the order of magnitude and changes in the size and how the size influences, here is an example of how particles settle in still air. So imagine a room totally enclosed, so no wind blowing, no air exchange, And if we release particles of different sizes from half a micron to 100 micron and let them float and see how quickly they fall, a particle of half a micron in totally still air will take 1,000 seconds. So that's more than 10 minutes, 15 minutes to settle only 1 centimeter. So that's a very short distance, while a particle of 100 micrometer will drop down this 1 centimeter in less than 0.03 seconds. So we see that this will really fall, quickly settle, will gone out of the atmosphere, while smaller particles remain suspended for a long time. If we add, this is all for ideally spherical particles with the density of 1 gram per cubic centimeter. If we increase the density, the particles of the same size will fall twice as fast. So particle of a density of 2 grams per centimeter cubic, so roughly sea salt, falls twice as fast as a particle of 1 gram per centimeter cubic, let's say water droplet or tiny water droplet or an organic material. So this is why size matters. Their behavior in the atmosphere is significantly dependent on the particle size and on the density. So we see here we increase the size by 10 times, but the settling velocity or the settling time decreases, or the settling velocity increases more than 2 orders of magnitude. So that's an important thing to also to note. Okay, so then the question is, which particle characteristic to measure? Particles can be characterized by the mass or volume concentration. So what's the total mass of the particles that are suspended in a unit volume of air? So that would be expressed in milligrams per meter cubic if it's mass, or volume micrometers per cubic micrometers per meter cubic. And that's sort of one of the measures of the particles. But on the other side, number concentration can also be really important. And that's expressed as the total number of particles per unit volume, per meter cubic, but more common per centimeter cubic. And also we could look at the composition versus of the particle, single particle, or the whole assemble of particles per cubic meter. So what's the amount of sea salt that we have, milligrams, or ammonium sulfate, or some organic, but also other physical properties such as particle surface area concentration could also be important. So particles with a different surface area concentration will have also different properties, and importantly, will significantly influence, could influence the particle toxicity as well. So this is another metric. So mass, surface, and volume. So why is this important as well, and what to measure and when? A good example and illustration of that is if we plot the dependence of these properties, number, surface, or volume of the particles, i.e. mass, versus their size. And we look at the typical size distribution of atmospheric particles. So this is the size in micrometers. So this is 100 nanometers or 0.1 micron. This is 1 micron, and this is down somewhere at 10 nanometers or 1 nanometer, sorry, or 0.001 microns. And we see that in the atmosphere, the particles typically, the biggest number of them are somewhere around above 10 nanometer, let's say 20, 30, 40 nanometer in size, and there's another mode somewhere here at around 100 nanometer size. We call this the nucleation and the accumulation mode. But if we plot now for these same particles the surface area distribution, so again, the size of the particle on the x-axis and the surface area, so of each of these particles on the y-axis, we see now that the peak, or the mode, sorry, moves somewhere to above 100 nanometers. These are the same particles, but we see that the majority of the surface is in these particles, which are larger. And if we do the same thing, and now another sort of mode appears somewhere in the micrometer size range. If we do the same thing in volume or mass, we see that this now mode in the micrometer size range, which was almost invisible in the number, becomes dominant. So if the importance is on number, then we need to measure the small particles. If the importance is on mass, then the small particles almost don't contribute at all to the total particle mass. It's the larger stuff. So what we'll concentrate here is on the small stuff, and we'll introduce instrumentation that's capable of measuring the small particles, so the number concentration of particles. So how to measure number concentration? Well, the simplest thing is to use the property of particles that they scatter light. So if light comes onto a surface of a particle, it will be scattered back depending on the composition and the refractive index. It can refract through the particles, come to a next one, scatter away. So when a particle light beam is in front of the observer, it scatters light, so less light comes in front to the observer. So a simple way to utilize that is to have a narrow beam of light and pass a particle in front of the narrow beam and have a detector on the other side. So when a particle passes in front of a collimated laser beam, like a laser, it will reduce the amount of light that forms on the photodetector, and we get a dip or a negative pulse. And then you produce a steady flow, counting the number of pulses per second, multiply that by flow rate, and you would get your particle number concentration. So how many particles per cubic centimeter. These devices are called optical particle counters, and they are the simplest possible devices to measure the light. And we can see that larger particles will block more light than small particles. And some devices even used to measure the intensity of these pulses, and from the intensity of the pulses estimate the particle size. Advantage, these are simple instruments. Lasers and detectors today are cheap. The disadvantage would be that they can only measure large particles. And this is some typical optical particle counters, commercially available. They're small handheld devices. They can be miniaturized. So this one is, I think, maybe 5 centimeters or 10 centimeters by 5 centimeters, very light, can be flown even in drones, etc. And that's what they do, and can be portable to larger devices, but they're mainly handheld devices. So we said the limitations of the particle counters are sort of twofold. There's the limitation on the amount of light the particle scatters. The smaller the particles, the less light it scatters, and if the particle is sufficiently small, it won't scatter any light, or light will be within the noise. The other limit is on the number of particles or the concentration that these counters can pass. So what's the limitation? If in our sensing volume two particles appear at the same time, so they both enter the beam at the same time, instead of getting one pulse for each particle, we'll get one beam, one pulse for both particles, a bit distorted, and that will be counted as one pulse, or one particle instead of two. We call this coincidence error, so coincidence of two particles appearing in the sensing volume at the same time. So the limitations on the particle size is that the amount of light the particle blocks, it's called the single scattering albedo of the particle, is not always equal to the cross section of the particle. But if the particle is large enough, and this is for different colors, the cross section of the amount of light the particles block isn't dependent on the size. This is some normalized size of the particles. But if the particles are small, light sort of scatters around the particles, and the particle doesn't block. The amount of light the particle blocks is not proportional to the surface area, cross-sectional surface area of the particle, but is smaller, and that's this light scattering albedo, and we see that significantly drops with the size of the particle. So particles at 0.1 of micron or 100 nanometer scatter about 3 or 4 orders of magnitude less light than larger particles of 1 micron. So they're hardly detectable below 100 nanometers. And this is roughly, this depends on the wavelength, but this is roughly the cutoff point for most particle counters is around 100 nanometers. So you can't measure particles smaller than 100 nanometers. But that could be a problem if we go back to our size distribution. We see that the majority of the particles are actually smaller than 100 nanometers. So if I use just an optical particle counter to measure the total number of particles, I'll miss all of these very small particles. So what do I do in that case? Well, a simple way to do that is you start with your very small particles, let's say they're all smaller than 100 nanometers, and you somehow expose them to saturated vapor, or actually somehow expose the particles to saturated, supersaturated vapors of, let's say, an alcohol. And as the whole sample is left for some time, the vapor will start sticking onto these small particles, and the particles will grow to a detectable size, and then just pass them in front of a laser beam and then sort of count them. So this is a fairly fast process if there is an excess of condensable vapor, so less than a second. So the only trick is now how to force these vapors to stick on the existing particles, and how to do that in a controlled manner. So to understand that, let's see when use several concepts, physical concepts, to understand when do particles or when do vapors start to condense. So this is valid for any vapor, and essentially this is how cloud drops are formed. But in our case, we'll mainly concentrate on condensing alcohol vapors, as they are the most commonly used in these cases. So vapors will condense on existing particles, and the particles will grow once supersaturated conditions are achieved. So what are the supersaturated conditions? Those are the conditions when the vapor pressure of a vapor is larger than the saturation vapor pressure. So when you have more vapor in the air than the air can hold. So this is when this is larger than 1, condensation will occur. Or we introduce something called the supersaturation ratio. So how much, so this is capital S, but with small s, is how much is the saturation ratio above 1. So 1 would be maximum, and this is above 1. Translated this to water vapor, humidity of 100% corresponds to saturation ratio of 1. Everything above 100% humidity is called supersaturated conditions. So the question is how to achieve supersaturated conditions of any vapor. You just can't, it's how to saturate the air with any vapor. Well, the simple possible way is to cool the liquid down. So if we draw the saturation vapor pressure versus the temperature, and I think this is for water, we see that there's an exponential dependence of the saturation vapor pressure. So the smaller the temperature, the smaller the saturation vapor pressure. The larger the temperature, the larger the saturation vapor pressure. So if I start with a, let's say, air mass or a volume of air with a certain amount of vapor pressure, and I cool it down, I will be moving it along this line because this is non-saturated condition, so there's less water vapor than needed to start condensing. But if I cool it down, I don't change the amount of water vapor in the air, I just bring it closer and closer and closer, and at one moment we will reach supersaturated saturated conditions. Cooling it further down, I will produce supersaturated conditions. So simplest possible way to saturate the air with any kind of vapor is bring a certain amount of vapor in the air and then cool it down. And then the vapor, the molecules start to condense. But the question here is, do both small and large particles grow at the same time? So do we need the same supersaturation ratio to grow particle small as 10 nanometers to grow particle as big as, let's say, 100 nanometers. Now, to answer this, we introduce something called the Kelvin effect. So if we look at a flat surface, and let these be some molecules of a certain liquid, we can see that the molecules of a liquid on a flat surface are surrounded by a large number of other molecules up to a 100 degrees or a volume angle of pi, and that these other molecules are pulling back the central molecules and keeping it into the liquid by cohesive forces. If I bend this surface and put these same molecules into a smaller, into a particle, so the curve the top surface, I see that now the outside molecules are surrounded by a smaller number of other molecules which hold it into the liquid, which means that now there's a less of a cohesive force, attractive force acting on the molecule, and the molecule can more easily leave the surface area. That would mean to keep the same number of molecules in a droplet, I need to have more molecules surrounding, so when one leaves, one replaces, two leave, two replaces. Then I would have in a flat surface. And that's expressed through the Kelvin equation, which says that the saturation vapor pressure for a curved surface at a temperature T is proportional to the saturation vapor pressure of a flat surface times an exponent. And this is a positive exponent, which means that any curved surface will have a higher saturation vapor pressure than a flat surface. So to keep the molecules in a curved surface, you need to have a higher concentration of the molecules in the vapor phase to keep it in equilibrium. So what does this saturation vapor pressure of a curved surface depend on? Depends on the surface tension. These are all constants, temperature, and inversely proportional to diameter of the particle. So the smaller the diameter of the particles, and that's in denominator, the larger the exponent, and the larger the saturation vapor pressure needed to keep this particle of radius d stable. Temperature functions in both, so it's not straightforward, and I won't go into that. So at a fixed temperature, smaller particles will more easily evaporate than larger particles, or to grow and stick vapors onto smaller particles, I'll need a higher saturation vapor pressure. This is an example for water. So to keep a particle smaller than 5 nanometer water particle, you need a saturation ratio 3 times larger for a curved surface than for a flat surface. And that is also an important property of trying to condense and grow small particles. So how do condensation particles, going back to condensation particle counters, work? They used to measure the particle number concentration, usually for concentrations down to nanometer size range, around 3 nanometers roughly. The particle size, or the particle droplets, are enlarged due to exposing them to supersaturated conditions of a certain condensable vapor. These vapors can usually alcohol, butanol, ethyl alcohol, glycol, or can also be water in some cases. So this is called the working liquid of a condensation particle counter. That's the vapor that sticks on the particles. They grow and reach a certain size, which is usually around 1 to 2 microns, and then they're just brought into a normal optical particle counter, so they go in front of a laser beam and we count them. The number concentration is measured, so therefore, for all particles larger than the lower detection limit of the instrument. And the upper detection limit is determined by the geometry, usually is governed by the losses, either gravitational or settling losses in the tubing of the instrument. And here is an example of a butanol-based condensation particle counter. So a condensation particle counter that uses butanol as the working liquid. So how does it work? You've got the aerosol inlet, so the aerosol go in through here together with sample with the air. They expose, there's a reservoir of alcohol, of butanol inside here, and there's usually a wick, which is like a porous cloth, which is drenched in that alcohol. So the alcohol evaporates, so you get a fairly high concentration of butanol vapor in here. It's still not sufficiently high enough for the butanol to start sticking onto the existing particles because we don't have supersaturated conditions here. How do we achieve this supersaturated condition? As I said, the easiest way, cool down this whole air. So cool down the particles, aerosols, together with the butanol vapor. And that's done in the second part. There's a thermoelectric pump or a Peltier cooler. It cools down the air stream. The butanol vapor reaches supersaturation, starts quickly sticking onto the surface of the particles. They grow to around, I think, 1 or 2 microns roughly. They pass in front of a laser beam. They scatter light and the laser diode detects. So each particle is for 1 pulse. Usually the temperature in this butanol aerosol mixture ranges from 40 degrees in the heated saturator, cooling down to 70 to 27 degrees in the saturator. So differences from 13 to 20 degrees. Normally, the higher the temperature difference, the higher the supersaturation ratio, and the higher the supersaturation ratio, the smaller the particles that we can detect. So increasing the supersaturation ratio changes the size of the particle that we can detect. These are condensation particle counters based on alcohol vapor. So similar, very similar ones are for ethyl alcohol and also for butanol based and glycol based condensation particle counters. With the water-based condensation particle counters, they're slightly more complicated and it's a different principle that's used. So what they have is the aerosols enter the stream and they are first exposed to a cold region here. There's a water field, so there's constantly water dripping along the surface. This is a wick, similar thing, so a cloth type substance, and we constantly feed the water vapor which slowly drips down. So it sort of makes a concentration of water vapor fairly large in this part here. And then in the middle of this tube, so the aerosols is pushed upwards, they're exposed to a hot region. You know why you say, well, this is actually the opposite of a butanol or alcohol-based one. So the warmer it becomes, the higher the saturation vapor pressure, which means further away we would go into to supersaturation. So essentially, if you put it to hotter condition, you would dry it out. But it uses a property of water, that water will diffuse to the center of the tube faster than the heat will because of these hot walls. So the hot walls push the water molecules towards the center, while the air needs a longer time to pass the heat towards the center of the tube. So what you actually get in the center of the tube is a more sort of concentrated water vapor, so more a higher concentration of water vapor in the middle of the tube than you would get in the cold region, but still a smaller supersaturation ratio. And then you quickly cool it down, so you concentrated the water vapor towards the middle of the tube, cool it down, achieve supersaturated conditions, and water starts to stick on these particles and you get these tiny droplets. And again, same thing on the top, you have your optical particle detector which measures the particle pulses. Interesting that this water-based condensation particle counters can go as low as several nanometers. I think 3 or 5 nanometers can detect the particles. And so what are the limitations of particle counters? As we said, it's the smallest size they can detect, and this is an example of a counting efficiency curve. So for a particle counter, let's say at around 10 nanometers, we define the lower cutoff point as the size where the efficiency drops to 50%. So 50% of the particles larger than this size, 10 nanometers, can be detected. The rest can't. What does this depend on? This depends on the working fluid, so butanol, water vapor, etc. It depends, as we said, on the saturation, vapor pressure, or supersaturation that we can achieve, and also depends a bit on the composition of the particles. Some are more sort of stickier, some are less stickier, some can grow. Hydrophobic particles can't, small hydrophobic particles can't be detected in water-based CPCs, while small water-absorbing hydrophilic particles can easily be detected. And also another important characteristics of the condensation particle counters is the response time. So how quickly they can respond to a change in the concentration from 0 to 100 or 90%. And that defines how quickly they can see any fluctuations in the particle number concentration. And that depends on the mixing volume. So how big is that volume in which you have the saturator? So depending on this here volume, and how fast the flow rate is. So the faster flow rate, the faster the response time, and also and that's around of the order of seconds, as we see for typical butanol-based or other particle counters. Okay, so I'll continue with the limitations. So we were talking about the response time, and it's around a second. There are new type particle counters which can go down to 0.1 of a second, but they're different principle. We'll cover them here. How to increase the lower cutoff point of a particle counter? The alcohol butanol-based ones are limited to around 3 nanometers, but recently there's been development of the particle counters based on the ethyl glycol. The advantage of using the ethyl glycol is that they can go down to, the ethyl glycol can condense onto particles as small as 1 nanometer in size. And this is an example of the so-called particle size magnifier. Essentially, it's 2 particle counters in one. The first one actually is based on the ethyl glycol. So in the ethyl glycol, you produce this supersaturated mixture, mix it with the inlet air, and particles small as 1 nanometer grow roughly to around, I think, 10 to 20 nanometer in size, or about 20 or 30 nanometer in size. And then they can't grow fully. This is still too small to be detected. So then they're passed on to another particle counter, condensation particle counter based on butanol, where they fully grow now to 1 micron and more in size, and they're measured. So these particle size magnifier actually magnify that size between 1 and 3 nanometers, which you would say it's very small, but it's really, really important in understanding the nucleation processes. And the other way these particle size magnifiers can be used is by changing the saturation vapor pressure. You change the activation diameter, so you can actually get a size distribution of aerosols from around 1 to 10 nanometers. So in that very, very small size range, just by using a particle counter. Interesting devices. So overall conclusion, this is an example of various commercially available particle counters from different manufacturers. I'm not highlighting any of them. They are very versatile instruments. They cover particle size ranges as small as 1 nanometers with the particle size magnifiers. and the response time as short as 0.25 seconds. They can go to concentrations up to 10 to the 6 particles per cubic centimeter, so they can measure very high concentration. Depending on the application, the working liquid can be either water or various kinds of alcohols. Both have advantages and disadvantages. And nowadays they have miniaturized them significantly, so they can be portable. This is an example of a very stripped down version of a small particle counter, which can be flown on a drone, and this is below 0.5 kilogram, to large sort of lab-based units or handheld smaller instruments. So this is the particle counters is the starting tool for anybody who is interested in looking at measuring aerosols. They can be integrated into other devices such as scanning mobility particle sizers, but that's a different story for a different lecture. And overall, I'd like to acknowledge the Horizon 2020 VIDIS project, the Virtual Center for Distributed Atmospheric Sensing for Reduction of Pollution Pressure, under the grant agreement 952433 for enabling or supporting this course and these presentations. Thank you and goodbye.